Hi there. I would like to upload this recording for your reference for lecture 5, which I believe for those of you in class, you took this lecture with Dr. Fab. So in lecture 5, what we're covering are two different topics. Well, two major topics. The first one is atomic spectroscopy, and the second is how to analyze atomic spectroscopy using Bohr model. All right. So before we get started, we always have a quick review on the topic we covered before. So in lectures 3 and 4, we went through two fundamental quantum postulates. Namely, the first one is called energy quantization, or that's when we're talking about Planck's quantum hypothesis in lecture 3. What it states is that energy levels are quantized. It means it is not possible to put any arbitrary amount of energy into an oscillator of frequency mu. So I'm showing here the energy diagram for the quantized energy level using the quantum mechanical picture. So on the right hand side, we have the energy of any oscillator broadly defined must equal to n, which in this case, n can take any integer number, times h, which is Planck constant, and mu, that's frequency of that oscillator. All right, so for any oscillator, energy levels are quantized. So that's our first quantum hypothesis, that energy levels are quantized. Secondly, we talk about wave-particle duality of light on our Wednesday lecture, lecture 4. This comes from the photoelectric experiment by Einstein, which says a light of frequency mu consists of quantas of energy. So again, what it means is when we're talking about light or electromagnetic radiation in general, you should be thinking about two different pictures. On one hand, light can behave as a wave. We have frequency, we have wavelengths, we talk about light wave all the time. At the same time, you could also consider light being consists of photons. Each photon is one quanta, one packet of energy, right? So the energy of each photon equals to h mu. So in the photoelectric experiment, we went over this diagram. What it means is you have energy of the photon shine onto the surface of the metal. If the energy of the photon has more energy than the work function of that piece of metal, you will have electrons ejected with certain kinetic energy. All right, so that's the review part. And now we're going to start from our new topic today, which is talking about atomic spectrum. And this provides additional evidence to what we have discussed before, namely our quantum hypothesis. So when we're talking about atomic spectrum, we can directly see that energy levels in atoms are also quantized. So when we get started, let's look at the experimental setup. We'll be talking about two different types of atomic spectra. The first one is called emission spectroscopy. What it means is we start from excited sample. What it means is at the excited sample, or the initial state, it is already at a much higher energy level comparing to the final state. So in the emission spectroscopy, what we have is the energy going down from the initial state to the final state. Again, in the process of this delta E, it releases light, all right? And the light goes through the single slit and the prism, we got a spectrum on our detector. So what does this spectrum look like? Here is what we have. Again, on our emission spectrum, we're talking about light coming out from excited samples. So what that means is on the dark background, we have bright light. So these bright lines are the light that's being emitted by the excited sample. So let's draw out the actual picture. Right, so this is the energy diagram we talk about. Let's just assume we have 4 energy states. So these number of energy states can go all the way up to infinity. N equals to 3, N equals to 4. Let's just use 4 of them as an example. So on here, why we're having so many different lines? What it means is, say our sample starts in N equals to 4. And then we have several possibilities. So this sample can go down to N equals to 3, or what I call delta E 4 to 3. It can also go further down to N equals to 2. So we have another line that's going from 4 to 2. And the longest one is delta E for 4 from 4 to 1. All right, so each of these delta E equals to E photon equals to H mu. So for each of these transformations, you're releasing 1 photon, and the energy of that photon released gives you the frequency of the light that's being released. Again, what we mean here is that 2 pieces of the information. Firstly, for each transformation, E photon, or 1 of the photon, is emitted. In emission spectroscopy. All right, so it's being emitted, that's why we're seeing the bright line. Second piece of information is each line represents a specific delta E. So if we look at this spectrum, right, imagine we can just count the line and say 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 different delta E. So you can imagine this starts from N equals to 10. So 10 to 9, 10 to 8, 10 to 7, 10 to 6, 10 to 5, 10 to 4, 10 to 3, 10 to 2, and 10 to 1. All right. Likewise, we could have absorption spectroscopy or absorption spectrum. So the setup for the absorption spectrum is slightly different. We zoom it out a little bit. What we have now, instead of having the excited sample, what we have is just sample in its ground state. All right. So when we see its ground state, we see that N equals to 1. And by shining light, when we say white light, we're saying it's light of all frequency. Our sample is going to absorb energy. And the resulting spectrum is we have dark lines on a bright background. So pause a minute and think about it. When we say it's a bright background, it comes from the white light source. Dark lines tells you that E photon is being absorbed. And if we write it out as an energy diagram, what we have, you see, it starts, again, let's use like 4 different energy states as an example. And our initial state is ground state. And what we have is we have delta E, that's 1 to 2. Delta E, 1 to 3. Delta E, 1 to 4. Okay, so now we have these experimental observations, right? By looking at the atomic spectroscopy, atomic spectrum, we get an idea about what's the energy level differences between n equals to 1, n equals to 2, n equals to 3, and n equals to 4. By just reading the spectrum, we can deduct what are the energy levels. Now the question becomes, do we have a mathematical equation to describe the difference in energy levels in the atoms? So here we're going to introduce the Bohr model. It is a relatively limited model, but it's a highly useful. In the Bohr model, what we're hypothesizing is you have different atomic orbitals. And these atomic orbitals can hold various number of electrons. Say n equals to 1 can hold only 2 electrons, n equals to 2 you can hold 8 electrons, and so on. But how exactly is the Bohr model deducted, and why we're saying it is limited? So let's look at the first question first. How the Bohr model is being deducted. So this is going to be an interactive process. So I hope if you haven't done it already, take that blank copy of our lecture notes, and we can work on the derivation of the Bohr model together. Okay, so here we go. We're talking about the electronic energy of an electron in an atom. So naturally, we can divide our total energy into kinetic and potential terms. Right? There's nothing fancy. Like any energy, you can write it in kinetic term and in potential term. In this case, we're just talking about hydrogen atom, so the potential term is just a Coulomb interaction between an electron and a proton. All right. We can further rewrite our kinetic term and potential term to what exactly we mean. For the kinetic term, we have 1/2 mv squared. That's from the basic physics. V is velocity, me, that's the mass of the electron. For the Coulomb's potential, again, it's a Coulomb's force and times the distance between the nuclei and the electron. So we know the Coulomb's force between the nuclei and the proton is Q1, Q2, 4 pi epsilon naught r squared times r. And since we know that for the electron, Q1 equals to negative E, and for the proton, depending on whether it's a hydrogen or a helium cation or lithium cation, we have Q2 equals to V times E. And in this case, R, that's the distance between the electron and electron. So taking together, we can write our potential part as negative Z E squared over 4 pi epsilon naught R. So that's our potential term. So again, in this case, right, we have r, that's a distance between proton and electron, or we can also call it atomic radii. Here, epsilon naught, this is a constant. E, that's charge of the electron. And Z, that's the atomic number. So now we have a general form for energy equals to kinetic energy plus potential energy. And then we have expression for kinetic energy and an expression for potential energy. So combining equation 1, 2, and 3, we get a classical expression on the energy of hydrogen atom in equation 4. So that's E equals to 1/2 mass of the electron times velocity squared minus Z, E squared, E is the charge of the electron, Z is the atomic number, over 4 pi epsilon r, r is the atomic radii. All right, so this is the classical expression of energy. But we still don't know anything about like velocity, and we don't know much about the atomic radii. What else can we do? So here we want to introduce Bohr's hypothesis, the quantum part. In Bohr's hypothesis, it states the angular momentum, abbreviated in big letter L, of electron movement is quantized in the atom. Or he simply declared that L, the angular momentum, equals to n, an integer number n, times Planck constant over 2 pi, where n equals to 1, 2, 3, and so on. So now we can solve for these quantized energy levels and quantized atomic radii. To do that, we'll need some classical physics information. So I'm going to give you that information here. So given with classical physics, we have L equals to MEVR. So here L is the angular momentum. Remember that equals to NH over 2 pi. That equals to ME, the mass of the electron, times velocity, times atomic radii. So now we can solve for velocity using these two equations here. So what we have is MEVR equals to L equals to NH over 2 pi. Solve for velocity in this relationship. We have V equals to NH over 2 pi MER. So this is our equation 7. All right, so we have an expression of velocity being quantized. A little bit more information from classical theory that we know the acceleration of an object in uniform circular motion, which is how the electron is circulating the proton, to has the magnitude of v squared over r. All right, so what we have is also given that a, let's just use the absolute value, we're not talking about direction here, equals to v squared over r. Also, in force, this is from Newton's law, force equals to mass times acceleration equals to me v squared over r. So this is Newton's law. And we also talked about the actual Coulomb's equation here. The force equals to z e squared over 4 pi epsilon r squared. Again, we don't have negative sign here because we're taking the absolute value. So this is the Coulomb's law. So now what we have several information here. We have velocity equals to nh over 2 pi me over atomic radii. That's our equation 7. We also have this term, right? So these two terms are equal to each other. So writing that out, we have F Coulomb equals to me v squared over r, that's from Newton's law, and at the same time equals to v squared 4 pi epsilon naught r squared. So now we can solve for the atomic radii by plugging these two equations. So what we have here, the velocity, we're going to write into this velocity term. And taking together what we have is me times n squared h squared 4 pi squared me squared r squared times 1 over r. That's the left-hand side of the equation. On the right-hand side of the equation, we have z times e squared 4 pi epsilon naught r squared. All right, so nothing fancy. We're just rewriting the term here. And now we can cancel out some of the terms on both sides. Right, so this me is going to cancel out with one of the me on the bottom. 4 cancels out on both sides. One of the pi cancels out. The r squared cancels out. So what we actually have after canceling out the terms equals to n squared h squared pi mer. That equals to the e squared epsilon naught. Since we're solving for atomic radii, as quantized, solve for r, what we have is Rn equals to n squared h squared epsilon naught over z e squared pi me. All right, so in this case, we have our Bohr radii, our equation for the atomic radii using the Bohr model. In this case, n equals to 1, 2, 3, etc. This is our equation 11. And for simplification, in this case, right, we have n that's the quantized level, h is a Planck constant, epsilon naught, that's a dielectric constant, E is the charge of the electron, that's a constant, pi is a constant, mass of the electron is a constant. So we define Bohr radii to be A naught equals to h squared epsilon naught e squared pi me, which is roughly equals to 0.529 angstrom. And then with a simplified version, we have Rn equals to n squared over z times the Bohr radii, with n equals to 1, 2, 3, and so on. All right, so this is what we have. It's called the radii for 1 electron atoms. Okay, so now we have the atomic radii. Next step, we want to solve for the quantized energy levels, En. So again, here we're going to use some of the equation we already know. So from equation 4, we have energy equals to 1/2 MeV squared minus Z E squared 4 pi epsilon naught R. From equation 11, we have Rn equals to n squared h squared epsilon naught Z E squared pi Me. This is what we just solved here. We also have equation 7 for the velocity, if you remember. Velocity equals to nh over 2 pi mer. So this is, we're just going to do lots of plug-in terms here, right? So the Rn